Hey kids, Charlie Abuso back again. We're going to do phases class number 2, which is really short, from number 24 only to number 36. You're going to need pencils in your notes. We're going to start drawing some of these heating, and we're going to draw cooling curves today too. Here we go. All right. So it says here we're going to draw what's called the cooling curve for rubidium. Cooling curve for rubidium. Now, rubidium is an element on the periodic table. We're going to need to get out table S because there's some numbers that we're going to have to get. Cooling curve is a title. The temperature scale is on the y-axis. Rubidium is element 37. It has a melting point of 312 Kelvin and 961 Kelvin is the boiling point. And then we got this chart. Now, cooling curve starts out really hot. It has to start out hotter than the boiling point because it's going to start out as a gas. Even though rubidium's a metal, it's going to be crazy hot because it's going to be a gas. And then we're going to remove heat. Now, across the bottom, there's a mistake. I'm going to fix that right now. Heat has to be removed. I can't actually fix it on this particular computer. I'm sorry, but that word has to be heat is removed at a constant rate. Apologize for that, boo-boo. We're going to label the dots in the segments A, B, C, D, E, F, and here we go. We start out above the boiling point. We have the boiling point, 961. We start out above at point A, and see at the bottom, it's fixed. Look at that magic. Heat is being removed at a constant rate. So as we're removing heat, the gas rubidium is cooling down, and it will get colder and colder and colder until that special point. In this case, it's not really the boiling point because it's getting colder. It's the condensation point. It's the same temperature as the boiling point, but in this case, because we're removing energy, it's going to go through the same phase change in the opposite direction. The gas will become liquid. So once it gets to B, the gas cannot get colder. If we remove any more energy from it, it begins to collapse into a liquid. It keeps its temperature, it keeps its kinetic energy, but the phase will change. So once we get down to B, if we keep removing energy, we get flat for a while. And as we're removing energy from B, where it's all gas, C is all liquid. So it's continually collapsing into a liquid. Once all of this rubidium is melted, is condensed into a liquid, only then will the temperature drop as we remove energy. From B to C, all the energy removal, all it does is change the gas into a liquid. There's no change in temperature. But at some point, in this case, it's point C, all of it is at the liquid phase. And if we remove energy, then it begins to cool down normally. And it will cool down and cool down and cool down. As we're pulling energy out, it will get colder and colder and colder. It's still pretty crazy hot because it's a liquid metal. Mercury is a liquid metal at room temperature, but this metal is still pretty hot. It will do that up until what's called the freezing point. Now, melting point, freezing point, it's the same temperature, but at 312 Kelvin, once rubidium gets down to 312 Kelvin, that's the coldest energy it can have, the coldest temperature, and remain in the liquid form. If we pull out any more energy, and we're gonna keep pulling energy out, it can't get colder as a liquid. It begins to turn into a solid. So from D to E, it changes from liquid to solid. At E, it's a complete solid. It's frozen. Now, 312 Kelvin, that's pretty hot, right? That's pretty hot. You'd be pretty warm in the summer at that temperature, but that's where it becomes frozen. And then if we keep removing any energy, once it's solid, then you could make it as cold as you like. And the arrow points downward, but it cannot go to absolute zero. That's very important. It goes towards colder, but it cannot get to absolute zero. Nothing can be absolute zero. Now I'm going to put that chart back in, and we're going to go through all the steps and make sure you understand what's happening at each step. Fill in this chart. Now from A to B, obviously the temperature is decreasing. And if the temperature is decreasing, the kinetic energy is decreasing. If the kinetic energy changes, we don't have any change in potential, only one energy changes at a time. Potential energy is really the energy of phase. And since A is a gas and B is a gas and there's no change in phase, there's no change in potential energy. So the first line looks like this. Temperature and kinetic energy are both decreasing. Potential energy steady, and gas, it stays a gas. Now from B to C, there's a change in phase. The flat part of the graph shows a change in phase. 961 Kelvin is the boiling point if it's getting hotter, but in this case, it's the condensing point. Now from B to C, the temperature stays 961. So if the temperature stays solid, if the temperature stays steady, the kinetic energy stays steady as well. But since we're removing heat at a constant rate, we must be able to describe what energy is decreasing. It's the potential energy, and that makes sense because gases at B compared to liquids at C, liquids have a lower potential energy. So the only way to go from B to C at a constant temperature with removing of energy is that you lower the potential energy, you lower the phase from gas to liquid. At C, it's all liquid. And as we remove energy, the temperature drops from C to D. The temperature's going way down. It goes from 961 down to 312. Temperature and kinetic energy both drop really fast. Potential energy has no need to change, and it doesn't because C is a liquid and D is a liquid. There's no change in phase, there's no change in potential. From D to E, though, that's the other flat part of the graph. That's the freezing point. Could be the melting point in the other direction, but it's the freezing point. It's going from the liquid to the solid. Now, there's no temperature change. At D, it's 312 Kelvin. At E, it's still 312 Kelvin. We remove energy, but the temperature doesn't change. All the energy removal does is it lowers the potential energy. It changes it from a liquid to a solid. So the potential energy decreases. And then from E to F, it goes from 312 down to as cold as you can make it, but not to absolute zero. The temperatures change, the kinetic energy changes, and there's no change in phase, so the potential energy is constant. Only one energy at a time will change. Temperature and kinetic energy work together. Potential energy is available for us during a phase change. Every single cooling curve for every single substance has this exact same shape. The only difference between the cooling curve for rubidium and the cooling curve, say, for water would be the name and the title. We'd have to change the title because this one's the cooling curve for rubidium. We'd have to change it to say water. And then the condensing point or boiling point would be 373 Kelvin, and the freezing point would be 273 Kelvin. But the shape would be exactly the same, and this chart would follow the exact same steps. A to B would still be gas, B to C would be the hot phase change, C to D would be all liquid cooling, D to E would be the cold phase change, and E to F would be the solid getting colder and colder, as cold as you could make it. Now, we're going to draw two curves on one graph. We're going to have double title, and it's plenty big enough to fit both of these on. Now, it says the heating curve for lead and the cooling curve for bismuth. Now, we're only going to draw one at a time. But the first thing we're going to do is we're going to look up the heating temperatures for lead. That means the melting point and the boiling point. So lead is number 82. We need to get these numbers written down, 600 and 2022 Kelvin. Those are the numbers for lead. Now, I wrote them in red. Bismuth is going to be black. You're probably using one color pen, so just do one at a time. Now, bismuth. Let's see if I can find it. 544 Kelvin is the melting point, and 1837 is the boiling point. So the first thing we do is we put these temperatures. See how I did this for you? The red temperatures are the lead temperatures, and the black temperatures are the bismuth temperatures. Now, the temperature is always on the y-axis, and across the bottom, we have heat added or removed. Now, for the heating curve for lead, heating, we're adding heat, but For the cooling curve for bismuth, we'd be removing heat at a constant rate. So we have sort of, the bottom is heat added or heat removed. That could be time also. We could just call over time, this is what's going to happen. And on a heating curve, you add energy. And on a cooling curve, you remove energy. So we have the table set up. And I think I'm going to do the heating curve first for lead. So we pick a temperature higher than absolute zero, but below the melting point for lead, 600. So I pick point A. It goes up to the melting point and gets flat. And then from C to D, it gets heated up until it reaches what's called lead's boiling point. And from D to E, the temperature stays constant because all the energy I'm adding is going to blow it apart into a gas. And then once at E, we're all gas lead because it's really hot, we can heat it up even more, and you can make it as hot as you can make it. Take it to the sun and make it 1,000,000 Kelvin. Now, to do a cooling curve, we have to start out hotter than the boiling point. So we have to start out somewhere above 1837, anywhere above, anywhere, literally 1838 would be fine. But to make a pretty graph, we start above that somewhere, and it's going to come down from hot gas to the condensation point. Now, 1837 Kelvin for bismuth, that's the boiling point, but in a cooling curve, it's the condensing point. So you come down to the condensing point, it cools into a liquid at C on the black line. And then from C to D on the black line, the liquid bismuth is cooling down till it reaches D, which is the freezing point, 544 Kelvin. It freezes, and then from E, it's a solid. You can make it as cold as you want, but it can't reach absolute zero. These two curves, even though they're not curves, they're like little step graphs. They are pretty much mirror images of each other. Start low, go high, or start high and go low. The numbers are different on the y-axis. They have different melting, freezing points. They have different boiling, condensation points. But the same things are going to happen on these graphs as happened on the other. From A to B, on the black one, the cooling curve, A to B, the gas cools down. The temperature drops. Kinetic energy drops. Potential energy steady. On the red graph, from A to B, the temperature increases, the kinetic energy increases, and potential energy is steady. B to C on both graphs is flat. That's constant temperature. On the black graph, it's the condensation, but it's a steady temperature. And on the red graph, B to C is a steady temperature. It's the melting point. Both of these graphs are pretty much reverses. The only difference is literally the title and the actual temperatures, the melting or freezing point, the boiling or condensation point. And they follow the same two charts we've already filled in for heating and cooling curves. What happens at any step for potential or kinetic energy or temperature or phase? Pretty easy, right? Pretty easy. Now, here's a special note, and this is important. On the black graph, BC, the hot phase change, that's where it's condensing. That happens at a hotter temperature than DE, which is freezing. On the black graph, condensation is a longer line than freezing. Do you see how long BC is on the black graph compared to DE? Now, on a heating curve, the hot phase change, DE, is way longer than the cold phase change, BC. On the red graph, BC is short, but DE is long. The hot phase change is always a much bigger energetic event. It takes much more energy to blow a liquid apart into a gas than it does to shake a solid loose. Now, just so you know, we're going to get into the numbers in the next topic of chem. We'll actually do a lot of mathematics on this. But for water, it's 7.1 times longer. These are just little pictures. We're having some fun. This is a casual drawing here. There are actual perfect graphs. The amount of energy required to melt 1 gram of ice compared to vaporizing 1 gram of water at the boiling point, it takes 7.1 times more energy to vaporize than it. You can melt it in your hand, right? Ice, but you can't vaporize, even if you put boiling water in your hand, which would be stupid, it would burn you. But even if you could put boiling water in your hand, you couldn't vaporize it. The hot phase change, the one that happens on the higher part of the graph, that's a bigger, longer line than the freezing or melting part of the graph, the low step. The low step is short, the high step is long. You got to keep that in your head. Now, characteristics of solids, liquids, and gases, true or false? Nearly every substance can be solid, liquid, or gas. Absolutely true, right? Absolutely true. Nearly every substance. There's some exceptions like wood. Wood is a weird thing. It's common, right? You got wood in your house. You probably have some wood on your person right now in your bag, or paper is made of, it's kind of wood. It's a solid. If you try to melt it, it sometimes will catch fire and burn. It will combust before it will melt. But nearly every single element, if you're willing to change the pressure, can be solid, liquid, or gas. Where do we find most element melting points and boiling points? Table S. Table S is our friend. And where do we find freezing points and condensations or condensing points if we need them? They're on table S also. They're just the other words. A melting point and a freezing point is the same temperature. The boiling point and the condensing point, it's the same temperature. Except for water, which you're supposed to memorize. If it's not on table S, you're not supposed to know it. Don't worry about it. I have to give it to you. If I tell you the melting point and the boiling point for, I don't know, sulfur trioxide, if I give that to you, you can draw a heating curve and a cooling curve. But without those temperatures, you can't draw an accurate one. You could write melting point and boiling point and just draw the flat lines and not know the actual temperatures, but you are not responsible to memorize a whole bunch of numbers, right? Except for water. Water's freezing point and melting point, you have to know that, as well as the boiling point, which is the condensation point. We're almost done. We're going to fill in this chart and we're going to work straight across. Let's talk about solids. What about solids, the particle attraction? Particles attracted very strongly together, right? Do they move? Not so much. They vibrate. Solid particles will vibrate, but they don't really move about. They stay together. They stay organized. The particles are, in fact, stuck together. The relative density compared to liquids and gases, almost always the solid is the most dense phase. There's some exceptions. And can you compress them? Can you squish a solid? Probably not. Hardly at all. Solids are already packed so tight together, there's very little oomph to get in there and squash them, okay? Almost zero. What about liquids? The liquid attraction is pretty strong too. Liquids stick together, but it's not quite as strong as the solids. The solids are stuck. Liquids are sticky. The particles do move. They flow over each other. They don't really get away from each other because they're sticky, but they don't actually get stuck. Once they're stuck, they become solids. That's what a solid is. A liquid and a solid are the same thing except for particle motion. We say the liquid particles are sticky but not stuck. Their density, usually medium, but usually it's actually very high also. You cannot squish liquids much because the particles are really close together as well. So you can't really compress them. Okay? The density for most substances, solids is the highest density, liquids is the second density, but it's still pretty high. It's a slight difference. Now, gas is completely different. Gas have practically no attraction. Now, particles are attracted a little bit. All particles are a little bit attracted together, but it's relatively weak compared to their energy of motion. So gases don't collapse into liquids. When we go to bed at night in the air, we don't wake up underneath liquid, right? The air doesn't turn to a liquid. The particles are bouncing around. Occasionally they'll stick together a little bit, but they bounce apart. They stay in the gas phase. Particle motion's crazy fast. The particles move at hundreds of miles an hour. They go in very straight lines only, no loop-de-loops and no curves. It's like geometry. And they have a lot of collisions and they bounce off of each other. The particles hardly ever touch each other except to bounce. Rarely do they ever get stuck together. I would bet much less than 1% of gas particles stick together at any moment. And then when they bang into something else, they break back apart. Occasionally molecules can get stuck together. They get literally tangled up. But then they bump into something else and they get untangled. Gases stay in pieces, little tiny particles flying around. The density is always much lower than liquids, much, much lower than liquids or solids. And gases can be compressed a lot. The spaces between the particles of gas is enormous compared to their size. In this giant classroom that some of you have never been to, I wish you would come in here with me. This is a pretty big classroom. All of the air in this whole classroom, if we squashed it a lot, would easily fit in my pocket, okay? The space between the particles is enormous compared to the particle size themselves. That's why I run so fast in the air, because there's practically nothing in it. But if I was in a swimming pool, I run really slow because the water particles are so close together, they hold me back. But in the air, I'm like Dash, right? I'm like Mr. Incredible's son, Dash. I could run so fast in the air, but in the water, I'm not so fast. And if I was buried in the dirt up to my hips, I couldn't run at all. Okay. Guess what? We're nearly done. 36. This is the last of it, the drawings. We're going to draw particle diagrams. Now, we did this a long time ago in matter, solids, liquids, and gases. Look what we got here. Solids on the left, the triangle. Particles are rigidly arranged. They're orderly. They're repetitively spaced. They have a definite shape. They do not take the shape of the container. You see how the container is bigger than the shape? The little solid chunk sits in the bottom of that beaker and does not spread out. But for liquid in the middle, the particles are at the bottom of the container. They're disorderly. They're actually moving. Can't show moving too well. They do take the shape of the container. They fill out in the bottom. Gravity pulls them down and they spread out best they can, but they keep moving. Now, gases on the right, the particles are in really fast motion, right? They only touch if they bump, and that's hardly ever, and they never touch the bottom unless they're bouncing off of it. They fill up the space of any container they're in. A little bit of perfume goes a long way. Now, at some point, you might have so little gas of perfume in such a big room, you might not be able to smell it anymore, but it's there. Just because your nose is not good enough to pick up one molecule in a billion doesn't mean it's not there. Gases will spread out and fill up any space you give them to. Solids, liquids, gases. These are particle diagrams. And there we go. We're done. Chemistry is great. It's nice being a teacher. I hope you're enjoying this. All right. This is not hard. It helps explain how the world works. All right. Beautiful stuff.